Swayam Prabha. Digital India. Educated India.
Welcome to lecture 8 of this course. In the last class, we discussed the harmonic oscillator problem and we saw how to quantize a harmonic oscillator by the canonical quantization procedure. The same strategy we are going to apply today in this class for quantizing a propagating electromagnetic wave. So let us begin. The strategy for quantization of classical system we adopt was suggested by Dirac, and this is called canonical quantization method. The strategy for quantization is as follows. First of all, find the Hamiltonian of the classical system Once you find the Hamiltonian of the classical system, then look for appropriate canonically conjugate variables. By canonically conjugate variables, I mean, say we have canonically conjugate variables, say eta and chi. These are canonically conjugate variables provided they satisfy the so-called Hamilton's canonical equation of motion. So say eta, it satisfies del H del chi, and chi has to satisfy this equation, that is minus del H del eta, or vice versa. So then eta and chi would be called canonically conjugate variables. Once I find out the canonically conjugate variables, it is also easy to find that they are going to satisfy the Poisson relations of this type. Eta chi is equal to 1. Okay, and then once I dig out the canonically conjugate variables, and then quantization is straightforward. This classical Hamiltonian would be now represented by this operator, and this eta chi, this Poisson bracket relation, would be replaced by the so-called commutation relation in quantum mechanics, and eta and chi would now take the form of operators, and that would be equal to is cross. So this is basically the procedure for canonical quantization. If you remember that in the last class we considered this mechanical harmonic oscillator, this classical harmonic oscillator, a mass m is attached to a spring or spring constant k. Then the Hamiltonian we wrote was, say, p square by twice m plus half m omega square q square, and q is the position and p is the momentum, and we know that that this q and p are canonically conjugate variables because they satisfy these Hamilton's canonical equation of motion. Okay, and they satisfy this Poisson bracket relation, qp is equal to 1. Then quantization was straightforward. This Hamiltonian then we replace by this operator, and then this is what we wrote. Both these variables p and q now take the form of operators, and this commutation relation, this Poisson bracket, is now replaced by this commutation relation between q and p, and that is equal to is cross. That is what the procedure that we discussed in the earlier class, and the same kind of strategy we are going to apply for quantization of electromagnetic radiation as well. Now discuss quantization of electromagnetic fields. We know that the electromagnetic fields has two components. One is the electric field and the other one is the magnetic field. So here E I'm referring as electric field and B as magnetic field. If I consider an electromagnetic field in free space, they are going to be described by the so-called Maxwell equations. So the Maxwell equations for an electromagnetic field in free space are given by this: divergence of E is equal to 0, curl of E is equal to minus del B del T, and divergence of B is equal to 0, and curl of B is equal to 1 by C square del E del T. I am sure all of you know these Maxwell equations without any charge and without any current, because I am considering electromagnetic field in free space. These are the Maxwell's equations. Okay, and I hope you know that this delta, this is a vector operator, this differential operator. This is in Cartesian coordinate. This is defined as, it has three components: x cap del x plus y cap del y plus z cap del z. These Maxwell equations has many solutions subject to the boundary conditions, and these solutions are called modes. By a mode we refer to a field that oscillates at a well-defined frequency. In fact, we'll see later on that when we'll quantize these classical electromagnetic fields, that these modes oscillates like a simple harmonic oscillator. There are many different kinds of modes, but we'll first consider traveling wave modes. We'll consider first traveling wave modes. Later on, we'll discuss the case of standing wave modes as well. And these traveling wave modes describe freely propagating wave given by, say, electric field expression like this. So a traveling wave is described by this electric field defined like this. I will explain the terms after writing this. So we have, this is the complex conjugate. This part here E0t refers to the complex amplitude of the electric field, and eta is the direction of the electric field, and it is known as the so-called polarization of the electric field. And k is the wave vector or propagation vector of the electric field, and it gives the direction of propagation of the electric field. And this is a solution of the Maxwell equations provided it satisfies certain conditions. Firstly, that this polarization or the electric field direction, or this polarization has to be perpendicular to the propagation direction. That is easy to see because we have this divergence of E is equal to 0, and if you actually put it these solutions in these Maxwell equations, you can maybe already you know that I can write it as k dot E as well. So k dot E is equal to 0. So therefore quite clearly it means that it is k dot eta E0 e to the power I k dot R. Okay, so this would be equal to 0. So that implies that k dot eta, the polarization direction or electric field direction, this dot product is 0. So therefore eta has to be perpendicular to the electric field direction, has to be perpendicular to the propagation direction. And this E0t, this characterizes the amplitude of the field which oscillates at a particular frequency with an angular frequency, say omega. Its solution is given by, we'll establish it little bit later using the Maxwell equation. So this is the solution subject to the condition that here omega is equal to Ck. All right, and now coming back to the concept of mode, by a mode is characterized by this electric field direction or the polarization eta and the propagation vector k. To explain it a little bit more, for example, if I consider, say, my propagation vector is along the z direction, so therefore you have your x and y components are 0 and it has, say, k is the magnitude of the propagation vector. Then the polarization vector has to be, it has either, it should have x component or it should have y component. So this defines one particular mode. And if the polarization vector is, say, along y cap but the k remains the same, that is going to be a different mode. Okay, or say k is along the z direction but with a different magnitude, then also this is going to define a different modes, because k dash is equal to omega dash by c, and here you have k is equal to omega by c. Say this is mode 1, this is mode 1, this is mode 2, and this would be mode 3, and so on. So we can have infinite number of modes like this. So I hope the idea of mode is clear to you. So in general, a mode is an elementary oscillating solution of the Maxwell equations, and mode determines the structure of the field. However, please note that this E0t, which is the complex amplitude of the electromagnetic wave, it characterizes the state of the field in a given mode. So let me write here E0t, which it characterizes the state of the electric field in a given mode. Okay, now going further, you see E0t is it's a complex quantity, so it's fully described by two dynamic variable. Dynamic because it has time dependency is there. It is described by two dynamic variables, and these are, say, real part of the electric, this amplitude, and another is the imaginary part of the amplitude. So these are the two dynamic variables, or in other words I can say that this is represented by the dynamic variable, the amplitude, magnitude basically, and the phase. So because I can write this complex quantity E0 t as, say, E0 magnitude and this is phase, right? So This is what I mean by two dynamic variables. And our goal is to look for these two dynamical variables which are canonically conjugate to each other. So to do that, let us begin our traveling with the traveling wave solutions and the Maxwell equations. Let me write again. The traveling wave solution I have here is this: eta E0 t e to the power I k dot r, and it has to have a complex conjugate because electric field has to be real, and we have these Maxwell equations. Divergence of E is equal to 0, divergence of B is equal to 0, curl of E is equal to minus del B del T, and curl of B is equal to 1 by C square del E del T. By the way, because these are plane wave solutions, so one can easily check that delta actually can be replaced by ik. Okay, and therefore I can say write this divergence of E is equal to, already I wrote that I can write simply as I k dot E, or curl of E del cross E, I can write it as I k cross E, and so on. Now let me use this Maxwell equations. Curl of B is equal to 1 by C square del E del T, because I already know the electric field. I have already assumed that electric field is like this. So what about the magnetic field? So magnetic field I can find out from this expression. To do that, let me put the solutions, the assumed solutions of the electric field in this Maxwell equation. So if I do that, I will get delta I can replace by ik, and that would be B, and we will have 1 by C square. If I take the time derivative of this electric field, then I will get eta vector here, and E0t dt, and then I have e to the power I k dot r. Okay, I'm not writing the complex conjugate part because B is also has accompanied by complex conjugate. So we'll later on, when we'll find the expression for the magnetic field, I will just write down the complex conjugate part, because B also has to be a real quantity. It's a measurable quantity. Now let me take cross product on both sides by k cross B. Let me take I to the other side. Then I have 1 by I C square. Here I have k cross eta cap, and I have d E0 dt e to the power I k dot r. Alright, now we know this rule from vector algebra. I hope all of you know A cross B cross C is equal to A dot C B minus A dot B C. So let us use this one rule here, and then we will get it as k dot B k, and that would be minus A dot B, that is your k square, and this is B. Okay, and the other side I have 1 by I C square. I'm taking, yeah, that would be k cross E eta dE0 dt e to the power I k dot r. And you see that k dot B is equal to 0 because of the fact that divergence of B is equal to 0, which I can write it as k dot b, I k dot b. So k dot b is equal to 0. So I can just do a little bit of manipulation here. So b is equal to, I can take minus sign this side, then I can have I by c square. Here I have k square, and then I have k cross eta dE0 dt. Okay, and then I have e to the power I k dot r, and I can therefore write my magnetic field as I can simplify, because I know that Kc is equal to omega. Okay, and therefore I have omega square k cross eta dE0 dt e to the power I k dot r. And because the magnetic field has to be real, so let me now put the complex conjugate part. So this is my magnetic field. Okay, now if you take the time derivative of this magnetic field and put it in the Maxwell equations, say curl of E is equal to minus del B del T. If I now take the time derivative and put it there, what I will get? Delta I can replace by I k, and this would be E. And here I have, let me just write it, I by omega square k cross eta. I am taking time derivative b, so it is d2 e0 dt2. Okay, I have e to the power I k dot r, and then I can also write it as I k cross eta. Let me just open it up here. I have here e0 t e to the power I k dot r, and then I have the other side. I have here minus I by omega square k cross eta d2 e0 dt2 e to the power I k dot r. Alright, so from here I can immediately get an equations for this amplitude d2 e0 t. I'm just writing it first here, dt2, and then this goes out. Okay, I goes out, then I just simply have it as minus omega square e0. So this is a second order differential equation. This equation is equivalent to two first order differential equations. They are dE0 dt is equal to plus I omega e0, and dE0 dt is equal to minus I omega e0. You can see that the solution of this equations are oscillatory. So e0 t, I can write the solution as say e0 at time t is equal to 0 e to the power or exponential plus minus I omega t. Okay, so one solution is associated with a wave traveling along k, and that is e0 t is equal to e0 0 e to the power minus I omega t, that is associated with a wave propagating along plus k direction, and another solution is associated with the wave going in the opposite direction. So this is the another solution, that would be e0 0 e to the power plus I omega t. Alright, but as we are interested only in one mode, we will keep only one solution, and that solution we are going to keep is e of t is equal to eta e0 0 e to the power I k dot r minus omega t. Alright, so this is the expression for the electric field. This is one mode we are considering, and the corresponding magnetic field would be B of, actually I should write here it as E of RT, and the magnetic field would be, you can easily show that would be k cross eta by omega E0 0 e to the power I k dot r minus omega t plus the complex conjugate. So what you see here, that both the electric and the magnetic field are actually in phase. So thus the dynamics of the electromagnetic wave propagating along this plus k vector, positive direction of k, is fully determined by these equations. dE0 dt is equal to minus I omega E0 of t. And that's the reason I said that E0t, the complex amplitude of the electric field, fully describe the state of the electromagnetic wave. Now, E0t, it's a complex quantity, so it is determined by two real variables, and we'll see that the real part of E0t and the imaginary part of E0t are canonically conjugate variables. This is what we are going to see soon. It will turn out to be canonically conjugate variables. Alright, of course within a multiplying factor, within a multiplying factor. So let us define E0t as say I, it's a imaginary number, some constant a, and alpha of t, where alpha of t is a dimensionless normal variable, and a is a constant. It's a constant having dimension of electric field, and this quantity is dimensionless normal variable, and it's a complex quantity. Okay, we are going to determine this constant later on. Now clearly, because E0t satisfies these equations, so automatically we see that alpha of t, this dimensionless normal variable, also satisfy this equation, that is d of alpha t dt is equal to minus I omega alpha of t. So this is a dimensionless quantity, alpha of t. So in fact this equation fully determines the dynamics of the it fully determines the dynamics of the electromagnetic field in the considered mode. Now if we introduce real and imaginary part of alpha of t, as I said that this is a complex quantity, let us introduce its real and imaginary parts. A real part is q and the imaginary part is say p, and it is multiplied by some factor, say 1 divided by twice h cross. We are still in the classical domain, but this h cross is the reduced Planck constant, and this multiplicative factor is there to simplify all the upcoming formulas simple. And clearly alpha's this conjugate would be 1 by twice h cross root, then you will have q minus ip, and from here one can immediately write these real variables q and p as in terms of alpha and alpha star as follows. It is very easy to get it from these two equations. From here you can write it q is equal to root over s cross by 2 alpha of t plus alpha star of t, and p would be h cross by 2 under root 1 by I alpha of t minus alpha star of t. You can easily verify it yourself. Okay, now let us write the energy of the electromagnetic field. So energy of the electromagnetic field in the given mode, energy of the electromagnetic field. So from classical electromagnetism or electrodynamics, you know that the energy, which I am going to represent it by the H, because that's is basically the Hamiltonian, that would be epsilon 0 by 2 the volume d3r, this, and then we have E square plus C square B square. This I am sure all of you know from classical electromagnetism. You can look Griffith's electrodynamics or any classical electrodynamics text to get this expression. In fact, this equation gets further simplified for traveling waves, because for traveling wave this first term and the second term are equal. So the total energy for traveling wave we can write the total energy as epsilon 0 d3r E square. Okay, let us now work out this integral. To work it out, let me consider a volume element. Say let us consider a cubical box having each side having length L. Let me first draw it. So we have a cubical box like this. This is x direction, this is y direction, and this is z direction. This is the origin, and each side has length L. And for simplicity, let us consider the electric field to be like this. Say electric field is polarized along x direction, and it has its complex amplitude E0t, and say it is propagating along y direction, along this direction. And then I have to add a complex conjugate so that the electric field becomes real. And quite clearly this electric field defines a single mode, and we are interested in a single mode. This I can further write, because E0t is a complex quantity. So E0t, this complex amplitude, I can write it as a modulus, and its phase say e to the power I phi. So if I want to write the full expression, I can write it in this particular form also. X cap twice E0 t, I can write it as cos ky plus phi. Alright, so this is the electric field expression we have. Now we are considering a traveling wave or a propagating wave. For propagating wave, it's going to satisfy certain boundary conditions. For example, the electric field at this wall along, say, here and here, actually this is valid for all other direction. What I mean to say, that the electric field at y is equal to 0 should be equal to electric field at y is equal to L. So if I impose these boundary conditions, you can see from these equations immediately that this is going to imply that I have cos phi should be equal to cos kl plus phi. If I open up the right hand side, I have cos kl cos phi minus sin kl sin phi. If I look at both the left hand side and the right hand side, then immediately I can say that this equation would be valid if I have sin kl is equal to 0. Okay, which is actually sine, I can write it as integral multiple of sine m pi. Okay, m is an integer, so it implies that kl should be equal to m into pi. You remember that k is equal to omega by c, so therefore I can further write that omega is equal to m into pi c by l. So this frequency get discretized because of the boundary conditions. And without loss of generality, let us consider phi is equal to 0 without loss of any generality. It's not going to affect our physics. So if I take that, then the electric field expression, I can write it as E is equal to x cap twice E0t cos ky. Of course, now we have these conditions as well, with kl is equal to m into pi, where m is an integer, m is equal to 1, 2, 3. Now let us evaluate the integral. H is equal to epsilon 0 e square d3r. Actually, this is a volume integral, so let me open it up. We are integrating over the whole cubical box. So x goes from 0 to L, y goes from 0 to L, z goes from 0 to L, and electric field I have here. Okay, let me just write here x cap. Okay, this is e square, so I have 4 here, and then I have, okay, let me write here e0t mod square cos square ky, and I have dx dy dz, and it is very straightforward to work it out. Let me just show you. For epsilon 0 0 to L dx 0 to L dz, and then this cos square ky, which I can write it as half 1 plus cos 2 ky dy, and this is from 0 to L. This integration is easy to, you can immediately get. I hope, yeah, I have to write here e0 mod square also. So I will have it as twice epsilon 0 e0t mod square, and if I this integral, immediately you will see that because of the fact that kl is equal to m pi, so if you put it in the limits, it's very straightforward to get it, then you will get it as the volume element. Integration dx dy dz is the total volume of the box. So this is what I have, the total energy of the traveling wave mode. I can express it like this. Now because E0t is equal to IA alpha of t, as we defined it like this earlier, we can write down this Hamiltonian in this form: twice epsilon 0 a square v mod alpha of t whole square. Okay, now this constant a, let us choose it like this: a is equal to h cross omega by twice epsilon 0 v. Let us, where v is the volume, or it is also called the quantization volume. In fact, if you look at this expression here, then a refers to the amplitude of the field that has energy h cross omega in the volume of quantization v. Okay, this is the meaning of this amplitude. So it is, let me repeat again, that this is the amplitude of the field that has energy h cross omega in the volume of quantization v. Okay, this clever choice of the constant makes quantization procedure simpler, as we will see now. Now with this choice of this constant a, this Hamiltonian, we can immediately write it as h cross omega mod alpha t square, right? So this is the form we get, where h cross omega, there is, we are still in the classical domain, by the way. In fact, here this h cross omega is the characteristic energy in the problem. Okay, now because you know that alpha of t, earlier we defined it like by this expression, it was 1 by square root of 2h cross q plus ip. So this Hamiltonian now takes this familiar form omega by 2 q square p square, and you can easily recognize this is the same form that we have for a harmonic oscillator. Now we are actually ready for quantization. The task at our hand now is to convince ourselves that Q and P are canonically conjugate variable. So we know that Q and P are canonically conjugate variable provided they satisfy the so-called Hamilton's equation of motion. So Hamilton's equation of motions for Q and P are as follows: Q dot is equal to del H del P and P dot is equal to minus del H del Q. So you can immediately write it as Q dot is equal to omega P and P dot is equal to minus omega Q. But to see whether these are meaningful or not, so let us say this is equation 1 and this is equation 2, and if I add equation on 1 and 2 such that Q dot plus say I P dot, then this would be omega P minus I omega Q. In fact, you can recognize that what I am actually doing is this is d of dt Q plus IP, and this I can write it as minus I omega Q plus IP. Now you know that Q plus IP is nothing but alpha, so I have d alpha dt, okay, and this is equal to minus I omega alpha of t. This is the same equation that we obtained earlier from Maxwell equations. Now we are getting it from the Hamilton's equation. So we see that clearly means that this Q and P are canonically conjugate variables, because we are able to derive a known dynamics of these variables. So Q and P are canonically conjugate variables. So because we established that these are canonically conjugate variables, we are now ready for quantization. In fact, quantization is a very straightforward business now. What we just have to do, we just have to Q will just you now replace it by operator, P also by operator, this like this, and then we will have this commutation relation between these operators. QP is equal to IS cross, and this Hamiltonian is now, can we write it as omega by 2 in this operator form. So we can, in fact, now you see this is exactly the similar form of the harmonic oscillator that we discussed in an earlier class. And now clearly we can introduce all the technology that we learned in the case of quantum harmonic oscillator in our earlier class, and we can introduce say alpha of t, say A, it is now an operator A, we can write it as 1 by 2h cross square root of 2h cross Q cap plus IP cap, and this alpha star t will now refer to A dagger. These are this is the your annihilation operator, and A dagger is the creation operator, and all these things we discussed already in an earlier class on quantum harmonic oscillator. One can immediately show that A dagger is going to satisfy this relation, this commutation relation will be satisfied, and the Hamiltonian we can express in this familiar form, that is h cross omega A dagger A plus a half. Okay, so this way we see that the mode of an electromagnetic wave oscillates like a harmonic oscillator. In fact, an electromagnetic wave consists of an infinite number of independent modes, and therefore we can write, if we consider all these independent modes, then the total Hamiltonian of the electromagnetic field, this we have just wrote for one mode only. If there are many modes, infinite number of modes are there, for one particular mode we have h cross omega lambda A lambda dagger A lambda plus half. Okay, and the corresponding energy expression would be E is equal to total energy. You just have to add it up, and that would be h cross omega lambda and n lambda plus half. All these things should be very familiar to you. Now for lambda-th mode, here this ket n lambda is called the number ket because it gives the number of photons number of photons or excitations in lambda mode. Please note that the electric and magnetic field which are observables in classical electromagnetism are now operators in quantum mechanics. So classical electric field that we wrote earlier was of this form. So it's the polarization direction. This is the complex amplitude E0t e to the power I k dot r plus complex conjugate. Now also note that E0t is, we write it as I a alpha of t. Now when we have quantized it, electric field has become now an operator. So I can now write it like this: eta E0t here I a, we have already taken h cross omega by twice epsilon 0 v under root, and alpha of t is now represented by this operator, annihilation operator. Then I have e to the power I k dot r, and this complex conjugate in quantum mechanics would be basically the Hermitian conjugate. Or I can write it as e cap I h cross omega twice epsilon 0 v under root, then this polarization direction. So let me write the full form: a e to the power I k dot r minus a dagger e to the power minus I k dot r. So this is the operator form of the electric field, and you can easily check that this is an Hermitian operator, and it has to be, because electric field represent observables. And similarly the magnetic field, so magnetic field can also be expressed. You recall that magnetic field, the classical magnetic field expression was like this for a single mode that we are considering here. That was k cross eta by omega E0t e to the power I k dot r plus complex conjugate. So now its operator form would be b cap rt, that would be I, you can easily get this expression, twice epsilon 0 v omega under root k cross eta, and then you have a e to the power I k dot r minus a dagger e to the power minus I k dot r. So electric field and magnetic field both now takes the form of operators in quantum mechanics. Let me stop for today. In this class, we have learned how to quantize a propagating electromagnetic wave. In the next class, we are going to discuss the case of standing electromagnetic wave followed by quantum states of radiation field. So see you in the next class. Thank you.